Imagine for a moment building something that needs to be incredibly sturdy. Maybe it's a towering skyscraper reaching for the clouds, or even something simpler like a reliable metal fence for your backyard.
Right.
What do both of those have in common? Their strength, their very integrity. It relies entirely on powerful, perfect connections. But what happens when those connections aren't quite perfect?
That's precisely what we're here to unravel today. We're taking a deep dive into the surprisingly critical world of, well, welding imperfections. And this isn't just about how a weld looks on the surface, It's about the fundamental safety and durability of structures that touch every part of our lives, often in ways we don't even see.
Absolutely.
Yeah.
Our mission with this deep dive is basically to comb through a stack of detailed sources on this incredibly important topic, extract the essential knowledge, and give you a real shortcut. A shortcut to understanding what can go wrong in a weld, why it happens, and what those hidden flaws mean for the bigger picture. Get ready for some truly eye-opening insights, I think, into the world beneath the surface of what might seem like a simple joint.
All right, let's dig in. When we talk about something being wrong with a weld, the sources make a really crucial distinction right at the start. They draw from standards like BSEN ISO 65201.
Okay. The difference between an imperfection and a defect. This feels like a critical piece of the puzzle, doesn't it, for understanding quality control?
It genuinely is. An imperfection is any deviation, any variation from the ideal weld. It's simply something that's not exactly as intended.
But not perfect.
Exactly. But a defect, now that takes a step further. It's an unacceptable imperfection. Think of it this way. Maybe a tiny scratch on a new car is an imperfection. You could live with it.
Right.
But a smashed windshield, that's definitely a defect. It's a deal breaker.
So it's all about whether that deviation actually meets a specific quality standard or if it poses a real risk. And just recognizing what you're looking at, that's the very first step, I imagine.
Exactly. And what's truly insightful here is that correctly identifying an imperfection is vital. It's really the only way to pinpoint the true cause of the issue.
Right, to figure out why it happened.
And then, implement effective measures to prevent it from happening again. It's not just about fixing one problem, it's about learning from it.
And speaking of learning, our sources categorize these geometric imperfections in fusion welding into 6 main groups. It's a fantastic roadmap for our deep dive today.
Yeah, it helps structure things.
Okay, so they are cracks, cavities, solid inclusions, lack of fusion and penetration, imperfect shape and dimensions, and finally, miscellaneous imperfections. We're going to walk through each of these, starting with what many consider the most significant threat of all.
Indeed. When it comes to threatening a weld's integrity, cracks are sort of in a league of their own.
Okay, why? Why are cracks considered so much more serious than, say, a tiny trap bubble or something? What's the fundamental danger there?
Well, it boils down to how stress is distributed in the material. A crack's geometry, especially that sharp tip, creates an enormous stress concentration right there. Imagine trying to break something with a blunt object versus hitting it with a sharp chisel.
Right, the chisel focuses all the force.
Exactly. That's what a crack does to stress in a material. It makes it exponentially more likely to cause a complete fracture compared to other, maybe rounder imperfections.
That's a powerful analogy. And our sources mention various types of cracks, too, depending on their orientation and where they pop up. Longitudinal, transverse, radiating, crater, branching. They can show up in the weld metal itself, the surrounding heat-affected zone. We'll call that the HAZ, right?
Yep, the HAZ.
Or even in the original parent metal.
That's right. The only exception among those is crater cracks. Those are found exclusively in the weld metal. But broadly, we classify these as either hot cracks, hydrogen-induced cracks, or lamellar tearing. Let's maybe tackle hot cracks first.
Okay, hot cracks. That sounds like they happen while the metal is still molten or, just starting to cool down. Is that right?
Precisely. There are 2 main types here: solidification cracks and liquation cracks. Solidification cracks occur right within the weld metal, often along its center line, as the weld pool cools and solidifies.
What's the main culprit for these? Is it just the metal shrinking as it cools, that pulling force?
That's part of it, but there's a key mechanism. Contributing factors include a high content of certain impurities in the weld metal. Think sulfur and phosphorus, those are big ones.
Okay.
Also, if the weld bead itself is very deep and narrow, what we call a large depth to width ratio, it becomes more prone. And any disruption in the cooling process, like an abrupt stop-start during welding, can trigger them. What's actually happening is these impurities gather and form thin liquid films along the boundaries of the metal grains as it solidifies.
Oh, okay.
Then, as the weld contracts from cooling, these fragile liquid films just tear apart. That forms the crack.
So preventing them seems to be about both the purity of the material and really precise technique.
Absolutely. The sources really hammer this point home. Avoid contamination. Things like scale, which can be high in sulfur, or oil and grease, which bring in carbon and sulfur.
There's no-nos.
Definitely. And you absolutely want to keep low melting point metals like copper, tin, lead, zinc well away from the weld area.
Got it. And how do liquation cracks differ from those solidification cracks?
Liquation cracks occur in the coarse grain region of the HAZ, so right next to the fusion line, very close. Imagine tiny pockets of impurity in the original base metal that actually melt at a lower temperature than the surrounding material. When the intense heat of welding hits that area, these pockets turn to liquid, sort of sweat along the grain boundaries. Then, if the material pulls, maybe from shrinkage stresses, they tear. They actually form as the material is heated up, not necessarily during solidification like the other type.
Okay, so hot cracks are about the metal's state during or immediately after solidification. But then there are these hydrogen-induced cracks, also called cold cracks or delayed underbeat toe cracking. Lots of names.
Yeah, lots of names for a nasty problem.
These sound a bit more insidious because they're delayed.
They are, and here's where it gets really interesting, I think. Hydrogen-induced cracking primarily happens in that grain-coarsened region of HAZ, often running parallel to the fusion boundary. The path it takes is usually a mix of cracking between the grains and cracking through the grains.
Okay.
But the truly critical insight here, there are 4 specific factors that must all be present, all at the same time, for HAZ hydrogen cracking to occur.
4 factors. Wow. That sounds like a perfect storm situation. And if you can prevent just one of those factors.
Precisely. You prevent the crack is a huge advantage for control. You need first a certain level of hydrogen in the weld metal, usually above 15 milliliters per 100 grams deposited.
Okay, hydrogen. What's that?
Second, significant stress within the weld, typically above half the material's yield strength. Third, the temperature needs to be relatively low, below about 300 degrees Celsius.
Right, that's why they're cold cracks.
Exactly. And finally, you need a susceptible microstructure in the HAZ. This often means a hard structure, say above 400 Vickers hardness.
So if even one of those 4 isn't present, not enough hydrogen, not enough stress, too hot, or the wrong microstructure, the crack simply won't form. That's a massive insight for prevention.
It really is. It means you can stop cracking by controlling any single one of those factors. For example, you can apply preheat before welding. That slows down the cooling rate, which helps prevent forming those hard, susceptible microstructures.
That makes sense.
Maintaining a specific interpass temperature between weld runs does something similar. Or you can use a post-heat treatment immediately after welding. This helps the hydrogen diffuse out, lowering its concentration.
Okay.
Then there's post-weld heat treatment, or PWHT. That reduces residual stress and can also soften those susceptible microstructures.
And it sounds like the choice of welding process and the consumables, the filler metals, plays a big role too.
Oh, absolutely. Using a process like TIG instead of, say, manual metal arc, MMA, generally results in much lower hydrogen levels.
Right.
Employing multi-run techniques instead of trying to do it all in one big pass can help too. It creates a self-tempering effect on the earlier runs, refining the microstructure, and gives hydrogen more chance to escape.
Interesting.
And even selecting specific filler metals, like austenitic stainless steel or nickel-based fillers, can avoid forming those susceptible microstructures in the first place, even if the other factors are present.
That's a whole toolbox of ways to tackle hydrogen.
Mm-hmm.
Okay, what about our final type of crack, lamellar tearing? It sounds unique.
It is, yeah. And its main distinguishing feature, visually, is its terraced appearance. And it occurs exclusively in rolled steel products, mostly plates.
A terraced appearance, like little steps in the crack surface. Why would a crack look like that?
It's due to a combination of factors. First, you have thermal contraction strain, the shrinkage pulling the steel plate in its through thickness direction, so perpendicular to the rolled surface.
Okay.
Second, and this is key, the steel contains non-metallic inclusions. During the rolling process, these get flattened into very thin platelets, lying parallel to the plate surface.
Ah, like tiny little weak planes.
Exactly. These inclusions are what create the steps. The contraction strain causes the steel to sort of debond around these inclusions, forming roughly rectangular voids. Those are the horizontal parts of the crack, the treads of the terrace.
Right.
And then further strain causes ductile shear failure between these voids, creating the vertical parts, the risers. That gives you that unique stepped look.
So how do you prevent something like that, given it's tied so closely to the material itself? Seems tricky.
Well, the sources point to two main approaches. One is simply using exceptionally clean steel with guaranteed through thickness properties, sometimes called Z-grade steel, which has very few of those inclusions.
Okay, better material.
Or, if that's not feasible, you rely on a combination of careful joint design to minimize those through thickness stresses, strict control over how the pieces are restrained during welding, and a well-planned welding sequence to manage the pulling forces.
Fascinating. So that covers the really critical world of cracks.
Hmm.
Now let's move on to our next big group, cavities. I'm guessing these are essentially just holes where they shouldn't be.
Essentially, yeah. Cavities are typically formed either by entrapped gas bubbling out of the molten metal or by shrinkage during solidification. The most common type we usually encounter is a gas pore.
So is that basically just a bubble of gas trapped inside this solid weld metal?
That's a good way to think about it. It's a generally spherical gas cavity trapped within the weld metal, and they can show up in different ways as isolated bubbles, maybe uniformly distributed throughout the weld, clustered together in one spot, or even forming linear chains or elongated shapes. And sometimes they break the surface, and we call that a surface pore.
What usually causes a gas pore, where does the gas come from?
Often, it's gas that shouldn't be there in the first place. Common culprits include damp fluxes or corroded electrodes. Moisture is a big source of hydrogen.
Right.
Or contamination on the surface from things like grease, oil, hydrocarbons, even just water. Air getting trapped in the shielding gas if you're using processes like MIG-MAG or TIG is another frequent one.
A leak in the gas line or something.
Could be, or just turbulence. Other reasons can include insufficient bioxidant in the filler metal to tie up oxygen, too high in arc voltage or arc length, or gas evolving from things like priming paints on the surface if they're not removed. Even using too high a shielding gas flow rate can sometimes create turbulence that pulls air into the weld pool.
Wow. Lots of potential sources.
Yeah, but the prevention, in most cases, is pretty straightforward. Keep materials dry, make sure surfaces are clean, check gas connections are secure, optimize your welding parameters. Basic good practice, really.
That makes perfect sense. Okay, what about wormholes? That sounds unpleasant.
They are, and they look pretty much like their name suggests. Elongated or tubular cavities caused by trapped gas escaping, occurring either singly or sometimes in groups. They often indicate a more severe gas problem than simple pores.
What causes those specifically?
They're typically caused by gross contamination of the weld preparation surface or maybe a laminated work surface where layers of the base metal separate and trap contaminants, or even crevices within the joint geometry itself that trap gas during welding.
So again, cleaning and material quality are key.
Fundamentally, yes. Thorough pre-weld cleaning, using unlaminated material, and maybe avoiding joint designs that create those gas-trapping crevices if possible.
And surface porosity then is just a gas pore that happens to break through the outer surface of the weld.
Precisely. It's a gas pore that manifests right on the weld surface. The causes are very similar to general porosity, damp, or contaminated surfaces, maybe low fluxing activity in the process, excess sulfur in the material, or loss of the shielding gas protection due to things like too long an arc or external drafts blowing the shield away.
Okay. Finally, within cavities, we have crater pipe. Definitely heard that term. It's that little dip or hole you sometimes see right at the very end of a weld run, correct?
Yeah, that's the one. It's a shrinkage cavity that forms right at the conclusion of a weld run, where the weld pool solidifies last. It's commonly caused by, frankly, a lack of welder skill, particularly when using processes with maybe too high a current for the stop.
Right.
In TIG welding, it can also be due to an inoperative crater filler or slope-out function on the machine. To properly fill the crater in TIG and prevent that pipe, you need to gradually reduce the weld current in descending steps until the arc extinguishes. It's a specific technique called slope-out, and it's crucial.
Got it. So from unwelcome holes, we move to unwelcome foreign objects. Next up, solid inclusions. The name kind of tells you exactly what they are, doesn't it?
It does. These are solid foreign substances that simply get trapped within the weld metal as it solidifies. By far, the most common type encountered is slag inclusions.
Slag, as in the glassy byproduct from the flux in certain welding processes.
Exactly that. Slag inclusions are irregularly shaped bits of slag that become trapped during welding. They look quite different from the typically spherical gas pores.
How do they get trapped?
Common causes include incomplete slag removal from underlying weld beads in multi-pass welds. You have to clean thoroughly between passes. Or sometimes the slag can flood ahead of the arc if the manipulation isn't quite right and the weld metal flows over it. They can also get trapped in irregularities on the work surface, like undercut from a previous pass. Now, a very fine dispersion of tiny slag particles might be present, especially with MMA welding, and might be acceptable. But it's the larger or sharply-edged inclusions that pose a real problem, as they can act as stress concentrators, a bit like cracks.
And flux inclusions are similar, but specifically from the flux itself, I assume, not the reacted slag.
Exactly right. Flux inclusions are literally trapped, unreacted flux powder or coating, so they only appear in welding processes that actually use a flux, like MMA, submerged arc welding, SRW, or flux cord arc welding, FCAW.
What causes those?
These can be caused by things like unfused flux falling into the weld pool from a damaged electrode coating, or simply when the flux fails to melt properly and gets enveloped by the solidifying metal.
Okay. What about oxide inclusions? Is that basically rust getting trapped?
Often, yes. Oxides trapped during welding are frequently from heavy mill scale or rust that wasn't properly cleaned off the work surface before welding. There's also a special type the sources mentioned called puckering, found especially in aluminum alloys. Yeah, it's caused by the tough aluminum oxide film on the surface getting folded into the weld pool due to poor atmospheric protection from the shielding gas and turbulence in the weld pool. It traps oxides inside.
Interesting. And then there's the unique one, tungsten inclusions, which I imagine only happen in TIG welding because that's where you use a tungsten electrode.
You're spot on. In TIG welding, tiny particles of tungsten from the non-consumable electrode can break off and become embedded in the weld metal.
How can you tell?
They're quite distinctive on radiographs, X-rays. Because tungsten is very dense, it absorbs more X-rays than the surrounding steel or aluminum, so they show up as bright white spots.
Okay. And what's truly surprising here, according to the sources, is the sheer number of ways this can actually happen.
Yeah, it's quite a list. Lay 'em on us.
Well, it can be as simple as the welder accidentally dipping the electrode tip right into the molten weld pool, or touching the filler metal rod to the hot tip of the electrode. Spatter from the weld pool can fly up and contaminate the tip. Exceeding the recommended current limit for a given electrode size or type can overheat it and cause particles to detach.
Okay.
Even things like extending the electrode too far out from the collet that holds it, or not tightening the collet properly, can cause overheating. Insufficient shielding, gas flow, or coverage, or excessive drafts that disrupt the gas shield are big ones, right? Letting the atmosphere get to the hot tungsten.
Exactly.
Or internal splits or cracks in the electrode itself can cause bits to break off. And surprisingly, even using the wrong shielding gas composition, like accidentally using an argon-oxygen mix meant for mag welding instead of pure argon for TIG, can attack the electrode and cause inclusions.
Wow, that's a lot of ways for a little piece of tungsten to end up where it shouldn't.
Yeah.
It really highlights the incredible precision and control needed in TIG welding, doesn't it?
It really does.
Okay.
Next on our list, lack of fusion and penetration. This sounds like the most fundamental problem you can have, the pieces just not sticking together properly.
That's the core issue, yeah. Lack of fusion is quite simply a failure of union, either between the weld metal and the parent metal at the side of the joint, or between successive layers of weld metal in a multi-pass weld.
Okay, so it can happen in different places.
Right. We talk about lack of sidewall fusion, lack of interrun fusion between the weld beads, and lack of root fusion right at the very bottom or root of the weld joint.
What typically causes that critical failure to bond? Why wouldn't it fuse?
Common causes include just not enough heat input. The arc isn't putting enough energy into the material to properly melt the surfaces that need to join.
Right.
Another issue can be when the molten metal floods ahead of the arc, especially in downhill welding maybe. It gets ahead of the heat source and solidifies before proper fusion can occur. Or, quite simply, the presence of oxide or scale or some other contaminant on the weld preparation surfaces can act as a barrier, preventing that metallic bond. For interrun fusion specifically, low arc current leading to a sluggish weld pool or too high a travel speed can be causes. And a lack of interrun fusion is bad because it also creates these crevices where slag can get trapped easily.
So it's really about ensuring the weld pool is both hot enough and clean enough to properly melt and merge with all the surrounding material it's supposed to join.
Precisely.
Then there's lack of penetration. Is that essentially the same thing as incomplete penetration? Are those terms interchangeable?
Yes, those terms are often used interchangeably. Lack of penetration basically refers to the difference between the actual depth the weld fuses into the base material and the nominal or intended penetration depth specified by the design. It just didn't go deep enough.
And what commonly prevents the weld from fully penetrating as intended?
A few things in the preparation stage can cause it. An excessively thick root face, the flat bit at the bottom of the groove, or an insufficient root gap, the space between the pieces.
Okay, setup issues.
Yeah. Or failure to cut back properly to sound metal when doing things like back gouging from the other side.
Yeah.
And just like lack of fusion, simply using too low a heat input can be a factor, as can using an MMA electrode that's too large in diameter for the joint or position that results in a lower current density at the arc, meaning less digging power.
Right.
It's important to remember, though, that sometimes partial penetration welds are acceptable, even required by design or code. But that's a deliberate engineering choice, not an accidental imperfection.
Okay, so incomplete root penetration would just be that specific issue, lack of penetration happening right at the very base or root of the weld, correct?
Exactly. In incomplete root penetration, both fusion faces right at the root are not melted and joined. If you were to look at the weld from the root side, you'd clearly see the original square edges of the root face still visible. The causes and preventions are essentially the same as for lack of root fusion, usually related to heat input, fit up, or welder technique just localized to that critical root area.
Moving on to our fifth group, imperfect shape and dimensions. Now, these might sound cosmetic, but I have a feeling they're often more than just about looks.
You're absolutely right. They're often far from just cosmetic issues. Take undercut, for example.
Undercut, that's that distinctive groove right at the toe of the weld where the weld meets the base metal, right?
Yes, exactly. It's an irregular groove formed right at the toe of a weld run, either in the parent metal or sometimes in previously deposited weld metal if it's a multi-pass weld. It's characterized by its depth, its length, and critically, its sharpness.
What causes it?
Common causes include melting of that top edge of the joint due to excessively high welding current or maybe too high a travel speed. Attempting to make very large single-pass fillet welds, especially in vertical or overhead positions, can lead to it. Excessive weaving or manipulation of the electrode or simply holding the electrode at an incorrect angle can also direct too much heat to that edge.
And I bet repairing it isn't as simple as just filling in the groove, is it?
Not at all, and this is a really important point the sources make. If you attempt a repair weld just to fill the undercut, you need exceptionally careful heat input control. If the bead you put down to fill it is too small, its cooling rate will be very fast. That rapid cooling can lead to increased hardness in the heat-affected zone of the parent metal right next to it, and critically, that makes it susceptible to hydrogen cracking. So a seemingly simple fix for undercut can inadvertently introduce a much more serious potential problem if it's not executed correctly.
Wow. Good to know. What about excess weld metal? That sounds like, well, too much weld material piled up. Is that ever a problem? Isn't more metal stronger?
It definitely can be a problem, and no, more isn't always stronger here. Excess weld metal is exactly what it sounds like. Extra metal that creates excessive convexity or bulge in fillet welds, or results in a weld thickness significantly greater than the parent metal in butt welds. It's only technically considered an imperfection if its height exceeds a specific limit defined by the standard.
Okay.
But what's fascinating here, and often misleading, is that the term reinforcement is sometimes used to describe this excess metal, particularly on butt welds.
Right, I've heard that. Weld reinforcement.
Yeah, but the sources are clear. In ordinary structural steel, this excess metal, this reinforcement, doesn't normally make a butt joint any stronger in terms of tensile strength. It might even weaken it in some ways.
So reinforcement isn't actually reinforcing. That's definitely a counterintuitive insight. Who knew?
It truly is. And what's crucial here is that it can actually become a significant problem. The sharp angle formed at the weld toe where that excess metal meets the parent plate creates a point of increased stress concentration.
Just like a crack tip, almost.
A very similar effect, yes. It significantly increases the risk of fatigue cracking initiating from that toe, especially under cyclic or dynamic loads. So in this case, more metal is definitely not always better and can actually be detrimental.
And then there's excess penetration, which I assume is like excess weld metal. But on the backside, the root side, of the joint.
Exactly. It's the projection of the root penetration bead beyond a specified limit. It can be localized, like little blobs, or continuous along the length of the weld.
What causes that? Too much heat again?
Often, yes. Causes include excessively high weld heat input forcing too much metal through, incorrect weld preparation, like having too large a root gap or too thin a root face or edge preparation can make it easier for metal to push through, or simply a lack of proper backing support during welding if required. Maintaining a uniform, controlled penetration bead requires significant welder skill, particularly in critical applications like pipe butt welding, where access is only from one side.
Got it. Next up, overlap. That sounds like the weld metal just kind of spilled over the edge without actually fusing properly.
That's a really good way to visualize it. Overlap is an imperfection right at the toe or edge of a weld, where molten metal flows onto the surface of the parent metal, but without actually fusing to it, it just sits on top.
Why would that happen?
It can be caused by poor electrode manipulation by the welder, maybe too slow a travel speed combined with high heat input, causing the molten pool to become too large and just flow outwards. Incorrect positioning of the weld, or even using the wrong type of electrode coating that results in excessively fluid weld metal can contribute.
Interesting.
And interestingly, in fillet welds, overlap is often associated with undercut, especially when welding in the horizontal-vertical position. Gravity can cause the weld pool to sort of collapse or sag downwards. This sagging action can create undercut at the top toe and overlap at the bottom toe simultaneously.
Okay, so the weld doesn't stick where it should, and it sags where it shouldn't. Makes sense. What about linear misalignment and angular distortion? These sound less like actual welding process problems and more like issues with how the pieces were put together before welding.
They are indeed structural preparation problems, rather than strictly weld imperfections caused by the welding process itself. Linear misalignment is when the two pieces being joined are parallel but aren't lined up correctly in the same plane, one's higher than the other.
Right.
Angular distortion occurs when their surface planes aren't parallel or at the intended angle relative to each other. The sources stress that even a small amount of misalignment can drastically increase local shear stress and bending stress at the joint when it's loaded.
So it really weakens the connection, even if the weld itself is perfect.
Exactly. Prevention is all about careful checking of alignment before welding starts, and the effective use of clamps, jigs, wedges, and tack welds to hold everything precisely in place during the welding process.
Okay. So the welding itself might be flawless, but if the pieces weren't lined up right in the first place, you still have a problem. What about an incompletely filled groove?
This is basically a continuous or intermittent channel running along the surface of the weld in the main body of the weld face, simply due to insufficient filler metal being deposited. The weld just isn't built up enough?
How is that different from undercut? Both are grooves, right?
Good question. It's important to distinguish it from undercut. While undercut creates a sharp, stress-raising notch right at the edge or toe of the weld.
Right.
An incompletely filled groove actually reduces the load-bearing capacity of the weld because there's simply less cross-sectional area of metal there to carry the intended load. It's a direct reduction in the strength of the weld itself, whereas undercut is more about creating a point where a crack might start.
Okay. Less metal means less strength. Simple as that. And irregular width. Is that just what it sounds like?
Pretty much. It's simply an excessive variation in the width of the weld bead along its length. It can be caused by things like severe arc blow. That's a magnetic phenomenon that can deflect the arc path unpredictably.
Right.
Or just an irregular weld bead surface, often indicating a lack of consistent welder travel speed or technique. While it might not affect the structural integrity in all cases, depending on the application, it can impact the width of the heat-affected zone, potentially reduce the load-carrying capacity if consistent throat thickness is critical, like in fine-grained structural steels, or even impair corrosion resistance in certain materials like duplex stainless steels where consistency matters.
Every detail truly matters, doesn't it? Okay, root concavity is next. That sounds like a shallow groove at the root, the backside, but it sounds like it's probably fused correctly, unlike lack of root fusion.
That's right. Root concavity, sometimes called suckback, is a shallow groove that can occur along the center line of the root of a butt weld. It's typically caused by shrinkage of the molten metal in the pool as it solidifies.
What makes it happen?
It can result from insufficient arc power or heat input to keep the root fully molten and filled. Incorrect joint preparation or fit-up, like too tight a root gap, can contribute. In TIG welding, sometimes excessive backing gas pressure can push the molten root bead inwards, causing concavity, Or, again, it can sometimes come down to a lack of consistent welder skill in managing the weld pool solidification at the root.
And finally, for this section, burn through. Yeah, that sounds exactly like what it is. The weld just burns right through the material, creating a hole.
Precisely. It's a pretty gross imperfection where the weld pool literally collapses, leaving an actual hole right through the joint.
What leads to that?
This usually indicates insufficient travel speed staying too long in one spot, or excessive welding current, just too much heat. Or again, sometimes a significant lack of welder skill in controlling the heat and the pool on thinner materials or root passes. Excessive grinding of the root before welding the second side can also make the remaining material too thin and prone to burn through. While it can usually be repaired, maybe by welding on a backing piece first, it's a clear sign of a significant issue in the welding technique or parameters that needs immediate correction. It shouldn't really happen with skilled welding.
We've covered a vast amount of ground so far. From those really critical cracks to the hidden cavities, the unwelcome inclusions, the fundamental failures of fusion and penetration, and the surprisingly impactful shape flaws. Now for our final category, miscellaneous imperfections. These are sort of the other damages and marks, but that doesn't mean they're not important, right?
Not at all. Some of these can be quite critical. Let's start with stray arc or arc strike.
Okay, what's that?
Stray arc refers to localized damage on the parent metal surface adjacent to the weld, not in the weld itself. It's caused by accidentally striking the arc or allowing the electrode holder, or even the current return clamp to make electrical contact with the workpiece outside the intended weld groove or joint area. It leaves these random little spots or areas of fused metal where they shouldn't be.
So basically zapping the metal in the wrong spot by accident. What's the big deal if it's not actually in the weld? It seems like just minor surface damage.
But what's genuinely critical here, and a key takeaway from the sources, is the hidden danger. An arc strike, even a brief one, instantly heats and then rapidly cools a tiny spot of the base metal.
Right.
This can create a very hard, brittle, heat-affected zone, or HAZ, at that spot. And crucially, this tiny hard zone may contain microcracks.
Oh.
And these tiny cracks, even if they're almost invisible, have the potential to grow under surface stress and lead to serious failures over time. Because of this significant risk, it's always considered much better practice to carefully grind off an arc strike to remove that damaged layer, rather than attempting to weld repair it by just melting over it. Trying to weld over it can sometimes trap those defects or make things worse.
That's a really crucial piece of practical advice. Grind it off, don't weld it over.
Okay.
Next, spatter. I've definitely seen that on welds, those little balls or bits of metal stuck to the surface nearby.
Yeah.
Is that just a cosmetic issue? Does it affect strength?
Well, while spatter itself, which are globules of molten weld or filler metal expelled from the arc during welding that then stick to the workpiece surface or surrounding fixtures, doesn't usually affect the structural integrity directly, it's often seen as more than just cosmetic.
Why is that?
Because its presence is actually a clear sign that the welding conditions are probably not ideal. Excessive spatter can be caused by things like using too high an arc current, too long an arc length, maybe experiencing a magnetic arc blow that makes the arc unstable, incorrect settings in gas metal arc welding, GMAW, or even using damp electrodes in MMA welding.
So if you're seeing a lot of spatter, it's like a red flag telling you something else might be wrong with the process, even if the spatter itself isn't the main problem.
Exactly. It often indicates other associated issues, maybe an excessively high heat input overall, or instability in the arc, which could affect fusion. While you can use anti-spatter compounds to make it easier to scrape off afterwards, its presence really signals that the overall welding process parameters probably need optimizing for better quality and stability.
Good point. What about a torn surface? That sounds quite violent. What causes that?
It is, potentially. A torn surface refers to localized damage caused by the improper removal of temporary welded attachments. Think about the small tack welds used to hold pieces together for assembly before the main welding.
Right.
If these temporary attachments are removed carelessly, maybe by just fracturing them off with a hammer blow instead of carefully cutting or grinding them, they can literally tear chunks out of the surface of the base metal they were attached to.
Ouch. How should they be removed?
The correct procedure is typically to carefully grind the attachment off, taking care not to gouge the base metal. Then the area should ideally be subjected to non-destructive examination, or NDE like dye penetrant or magnetic particle inspection, to check for any cracking caused by the removal. And finally, if necessary, the surface should be restored to its original shape, usually by light grinding or sometimes by welding using a qualified procedure if material was removed.
So it's another case where seemingly superficial damage can actually hide a structural integrity issue if not handled properly.
Precisely.
And finally, what are some of the other notable miscellaneous imperfections the sources mention? Just to round things out.
Yeah, they briefly list a few others. Things like grinding marks, just local damage from abrasive grinding wheels, chipping marks caused by using chisels or other impact tools perhaps during slag removal, underflushing, which is a localized lack of material thickness where maybe grinding has gone too deep.
Right.
Misalignment of opposite runs, where the center lines of welds made from opposing sides of a joint don't perfectly line up, and temper color.
Temper color.
Yeah, that's the lightly oxidized surface film, often showing blues and browns, that you commonly see on stainless steels after welding. It indicates the heat history, but it's generally not considered a structural defect unless it's excessive, maybe indicating overheating, which could affect corrosion resistance.
Okay, wow. We've now covered the full, pretty extensive spectrum of things that can go wrong in a weld, from the big ones to the small ones. So once these imperfections are identified, maybe through inspection, what's the plan? What happens next?
This brings us to the crucial questions. What's actually acceptable, and what needs to be fixed? Because weld imperfections, as we've seen throughout this discussion, can seriously reduce the integrity and safety of a structure.
Right.
Therefore, locating them reliably, usually using non-destructive examination techniques like visual, magnetic particle, penetrant, ultrasonic, or radiographic testing, then assessing their significance and figuring out how to prevent them from recurring are absolutely crucial steps before any welded joint is put into service.
So it's definitely not a free-for-all. There have to be clear rules, these acceptance standards you mentioned, that dictate what level of imperfection is okay and what's definitely not.
That's exactly right. The acceptable size and type of any imperfection are precisely defined by defect acceptance standards. These standards are usually part of broader application standards or specifications that are relevant to the specific industry, like pressure vessels, bridges, buildings, pipelines, or specific project requirements. These are essentially the rule books for quality control in welding.
And I'm guessing, based on our earlier discussion, that cracks are almost universally unacceptable, given how dangerous they are considered.
That's a critical point to underscore, yes. The sources are very clear. All normal weld imperfection acceptance standards totally reject cracks. Any crack indication found during inspection is typically cause for rejection.
No matter how small.
Generally, yes. Only in truly exceptional, very specific, agreed-upon circumstances, and usually only with demonstrable proof that the crack won't propagate and lead to failure, often involving complex fracture mechanics calculations and analysis, might a known crack be allowed to remain in a structure. But typically, discovering a crack means outright rejection of that weld section. It has to be repaired.
So no matter how tiny, a crack is usually a deal breaker.
Got it. And I bet these acceptability levels for other types of imperfections aren't universal, are they? A simple metal garden fence surely wouldn't need the same stringent standard as, say, a nuclear reactor component. Exactly. This is another crucial point. Acceptability levels vary widely. They differ significantly between different applications and service conditions, and sometimes even between different national or international standards for the same application.
So you can't just guess.
Absolutely not. This means you must always refer to and rigorously use the specific acceptance standard that is quoted in the contract or specification for that particular job. You cannot just pick a standard you like or one that seems easier. It's a contractual and safety obligation.
Okay. So once an unacceptable imperfection is found, based on the correct standard, what's the repair process typically involve? Do you just try and weld over it carefully?
Absolutely not. Welding over a defect is generally not effective and can trap the original problem. Unacceptable imperfections must be completely removed first.
How is that done?
Well, if it's a relatively shallow surface defect, like minor undercut or surface porosity, it might be possible to remove it by just superficial dressing. That basically means grinding it out smoothly without needing to add any new weld metal, provided that sufficient material thickness remains after grinding to meet the design requirements.
Okay, just grind it away if it's shallow enough.
Yeah.
But if it's deeper, like internal slag or lack of fusion?
If the defect is too deep for simple dressing, or if it's internal, it must be completely removed. This usually involves excavation, meaning you physically cut or grind out all the defective material and a little bit around it to be sure.
Okay.
And then new weld metal must be added to fill that excavation and restore the joint to ensure the minimum required design thickness and strength are achieved.
And I assume that repair welding isn't just done any old way.
Definitely not. Crucially, any weld repair, whether it's just filling a small excavation or sometimes remaking an entire joint section, must be done strictly according to an approved and qualified welding procedure.
Yeah.
The rigor involved in qualifying that repair procedure depends entirely on the application standard and the criticality of the component. Sometimes it might be a pre-approved standard procedure, but for highly critical applications, it might require an exact simulation of the repair on a test piece, make the joint, excavate the defect, refill it using the proposed repair method, followed by extensive inspection and mechanical testing, essentially proving beyond doubt that the repaired weld is as good as, if not better than, the original sound weld.
So it's a very controlled, very carefully managed, and often complex process to get it right.
Yeah.
It's definitely not just a quick batch job.
Precisely. It's all about ensuring the final repaired weld meets the exact same, if not sometimes even higher, standards of quality and integrity as the original design intended. Safety is paramount.
Wow, what a journey that was through the often hidden world of welding imperfections.
Yeah.
We've truly unpacked a huge amount today.
Mm-hmm.
Everything from those most critical, fracture-prone cracks
Mm-hmm.
to the insidious nature of cavities and solid inclusions, the fundamental failures of fusion and penetration that stop things sticking together, those surprisingly non-cosmetic shape flaws, and even those seemingly minor miscellaneous surface marks like stray arcs and spatter that can have bigger implications.
And if we connect all this back to the bigger picture, I think understanding these imperfections isn't just for the welding specialists or the engineers, It's really about appreciating the intricate science and the sheer level of precision that goes into ensuring structural integrity and safety in countless aspects of our built world.
Yeah, absolutely.
It's a testament, really, to how profoundly complex even a seemingly simple weld can be, and how much hidden knowledge and control goes into making the world around us safe and durable enough to rely on every day.
It truly is. So it leaves us with a thought, maybe. What does this all mean for the future? Given this vast array of potential imperfections we've discussed and all their complex interactions and causes, how might advancements in things like artificial intelligence and robotics revolutionize not just the act of welding itself, which we're already seeing,
Right, automation is growing.
but also the inspection and prevention of these very imperfections? Could we see AI-driven systems, perhaps with advanced sensors, that lead to even safer, more reliable structures in the future? Maybe by catching these flaws in real time as they form, or even predicting the likelihood of them occurring based on conditions and adjusting the process before they even happen.
That's a fascinating possibility. Real-time monitoring and predictive quality control.
Yeah, it's certainly something interesting to ponder until our next deep dive.